some warm messages from our well-wishers. And in the afternoon, we have 2 lab visits from 3 p.m. to 5 p.m. of 1 hour each. And thank you all for the overwhelming response that you have given online and we have received already. To those who haven't registered yet, this is a golden chance for you all to register once again for the lab visit. And to register, kindly please contact Mehak after this program. So once again, warm welcome for all of you to this program. Thank you. And the most awaited, as I have mentioned in the mail, like surprise games. Everyone was talking about that. Let's begin our surprise game. Take it as a fun, and as I told you, warm up your brains. And there are simple rules to follow in the game. You will be distributed 2 palm leaves, like 2 printouts. And each of the sheets consists of the game named Catch Me If You Can and Who Am I? The first one is a word puzzle where you have to find the words. And the clue is, let me keep it a secret, and let me see whether you need a clue or not after seeing the printout. And the other one, second one, it's the name of scientist which you can relate with the clues. These are all simple. As ma'am said, simple as it is. You can find it after some time. And winners will be announced after our talk of ma'am. And one more very important thing. Please keep all of your cell phone aside and let your brain try it. Okay, so let's start. Hope everyone is equipped with the pen and you want. So we will have 5 minutes to answer. And do you need a clue for the first one? Catch me if you can. Anyone? These are units, like 15 units in physics. That's the first part. And the second part, name of some scientist you can relate. And your time starts now. It's for 5 minutes. Please don't discuss. Please don't forget to write your name, okay? Oh, you need pen? No. The first one, catch me if you can. It's only the units. Not the scientist. Who am I is the scientist. And there are people who are in need of pen. Please keep your mobile phones aside, please. Who are in need of? Oh. I saw someone is working in team, so please mention your name then together. Okay, if that's the case, you can participate, no problem. You can write the name together then. Team will get a single prize. You can share it. And one more rule for the game. Those who are answering maximum number of questions will be the winners to make sure. Take it as a spirit. Participation is much more than winning prizes also. So give it a try. Warm the brain. Let's see whether you have forgot your basics or you forgot the great people who have led us this way. I can see the serious faces. Pardon me? Rules for? I said units in physics. You have only 20 seconds more. Yeah, crossways, diagonal, up, down. Yeah, anti-diagonal too, at times. So time up. Let's collect it. How was the game? There are words too. And do you feel like getting answers? No, we'll discuss about it when we are distributing the prizes. Let's see. Yeah, we have some fun comments too. So hope that everyone enjoyed. At least give it a try, right? I hope that it was a good try. So many said that they are not participating, and then I think they enjoyed the game. So thank you very much. And let's move to the important part of this celebration. Now, a leader is one who knows the way, goes the way, and shows the way. I invite Professor Urvashi Sinha to address the gathering. Ma'am, please.
Thanks a lot, Ashleen. I wanted to play the game, although I knew the questions. So thanks a lot. Can you hear me at the back, Mr. Varadarajan? Yeah. So today is a very special day. Personally and professionally, it's been 10 years since I joined RRI. 15th March 2012, I walked in here, met the then director, and since then, QuIC Lab started. So I'm very, very happy, very emotional, but also at the same time, very excited to share with you some of our journey. So I will tell you, so this is going to be a talk which is, not the usual type that I'm used to giving. So it won't be focusing too much on the details of the science and the techniques that we have done, but it's going to be a people talk. So I'm going to actually talk about the people who have made this happen and what they have enabled. So it's going to be the people and the science they have enabled. And I think, since it's 10 years, this is what I would like to share with you, okay? So what we work on is, of course, photonic quantum science and technologies. And we have been, of course, as you know, around for 10 years now at RRI. The mantra that we follow in the lab is, today's science is tomorrow's technology. So we tend to work on the fundamental aspects of the science and then, apply it to cutting edge technology as well. And so we do this hand in hand. And so I think, this is what we would like to continue doing as we go along, as time goes by. What is the big picture? Well, the big picture is a little bit bleak. As always, our theoretical understanding of the universe is very incomplete. I can see that we have a lot of people here who are not from our immediate background or even from the science background. So this is something maybe you don't know, that we are not aware of 80% of what the universe is made of. So it becomes very important to be well aware of at least what we think we know. And that is what forms a very important core part of what we do, which is fundamental tests of various aspects of quantum mechanics and quantum optics, okay? And then, of course, the applications, which are in the domain of quantum computation and quantum communication. And I will tell you a little bit about what these things are, to the extent that you will, hopefully go back with a certain idea. So we deal with experimental and theoretical problems in this holistic domain, okay? So what is our lab? Our lab is, of course, a quantum optics lab, and it is a class 10,000 clean room. And we have a very highly modulated environment, and some of you are coming for the lab visit in the afternoon, so you will meet some of the people there and also see some of the equipment and some of the science you will hear. So we work on different aspects of quantum information, computing, and communications, and this is our lab website. So going on to the main part, as I said, it is going to be about the people. So the first people who, of course, started the lab in that sense were the people who came for the inauguration. That was towards the end of 2012. So here you can see Raymond Laflamme, Gregor Weiss, and Thomas Genevine, who were the three people who I feel have been my colleagues, mentors over the last several years. And so they all came, and this is my representation of an experiment that I had done a long time ago on the 3 slits. So this was the idea, to have a 3-ribbon cutting for the lab, okay? And so this is a host of dignitaries who visited us, including our close collaborator, Barry Sanders. So all of them were there. Gilles Brassard of the BB84. So all of them came and started off a journey. But I would say the journey did not begin with this cutting of the ribbon. Actually began in March 2012, when I first came in, as I said. Our then director was Professor Ravi Subramanian. We exchanged pleasantry. Conversion of 2 storerooms to a quantum optics lab, which is a class 10,000 clean room, happened because of a lot of the people who are currently in the audience who are not from the academic section. So Mr. Suresh is here with us today. Thanks for coming. So he has now superannuated, but he was the head of this, estates and buildings at that time. And we wrote a 100-page document to actually motivate the need for a clean room. The then administrative officer required. We wrote that. So we are very pleased that now we have more clean rooms coming up at RRI. But then, of course, we were the first to make this happen. And so excellent coordination between the electrical section, the civil section, the security, of course, accounts and purchase, because all the equipment was bought during that time. So when we started the lab, when you walk in here, already the TIE Sapphire laser was there. And this happened because of the excellent coordination and support that I received from the various sections of RRI which came together to help us with our cause to build the lab. So this is how our journey began. And then, of course, this was the formal opening, so to speak. And now things look like this. Some of you will see this in the afternoon, where we have very nice experiments ongoing on different topics. And of course, as I said, this is a people talk, so I continue with that theme. These are, the current members of the lab, many of who are here today. And then, of course, these are some of the former members. All of them didn't fit, but then, so many people have contributed to what we are today. And the idea will be that I will tell you about some of the work we do in association with these people, okay? And of course, without the collaborations, we don't succeed. So it's a collaborative field. So we have a lot of collaboration both in India and abroad, and several people who have, placed their trust in us, collaborated with us on various topics, and I would like to acknowledge all of them today as well. So these are most of the current members of QuIC Lab. 1 or 2 were picture shy, I think, and so, but then I think we have many of them here. So you will see many of them also. Some of you are here, right? So then this is the current group. Anyway, so what do we do? So what we do is, of course, based on this field called quantum mechanics, right? And this is Richard Feynman. He was a Nobel laureate. I think most of you know him or know of him. He had said this, that he can safely say that nobody understands quantum mechanics. And so this was in 1965. But then, of course, a long time has crossed since then. But we can still safely say that we don't understand a lot of quantum mechanics. And it's not, Soumya, because you don't try. It's just that the field is this way, right? So it is just that when you feel you have understood something, some question comes up. And so that is what keeps it exciting. And all the applications keep it even more exciting. So these are all the various things that we use without thinking, which are based on quantum mechanics, right? So this is applications. But then this is a field which has had rich history and legacies. And, all these people here, Bohr, de Broglie, these are all Nobel laureates, right? So then, and it goes on, Thomson, Davison, and Germa. So it's not like you do quantum mechanics to win the Nobel Prize. That's not the message. The message is that it has had so much contribution over the last several decades that it has been honored even in this forum, with the highest prize in science. And it continues, Schrödinger, Dirac, Heisenberg, Max Born. So all these people and many more, okay? And of course, for the people who are not from the field, quantum mechanics, we can say is a field which deals with phenomena at microscopic levels, okay? So having said that, few of the concepts which you will find relevant, in also understanding a little bit of what we do, I wanted to discuss with you. One of them is what is called the quantum superposition principle. So now what is that? That is a very strange thing if you're not from our field. So it is like, having a light which is off and on at the same time. So what would we think? We would think that the light would either be off or on. But in quantum, you can have it a little bit off and a little bit on at the same time. And that is what describes superposition. And that is a quantum bit, which is a combination of a little bit of this and a little bit of that and a two-level system, okay? And that is what this quantum computer is based on. So, which we hear a lot about these days. So this is what I meant, that you have two states which are just distinct in the classical domain, 0 and 1, but you have all possible combinations possible in the quantum domain, right? And this is what happens when that happens. So if you have, let's say, two such systems, then in the classical scenario, you would have one in these four possibilities. Jacob would recognize this because it's the simple, classical computer is based on that, and he's our classical computing person. So you have 0, 0, 0, 1, 1, 0, 1, 1, right, Mr. Sridhar? But then in quantum, we can have all four at the same time. And so when it becomes more and more, say let's reach a number 50, then we have 50 possibilities in classical, but we have 2 to the power 50, which is possible in quantum. And that is a number which is proportional to the age of the universe. So this is where the quantum computer gains its power. The algorithms are based on this. They make use of this possibility. And that is what makes it such an exciting field. Okay. And these are various devices that people are, working on, different approaches towards building this quantum computer. And again, these are two people, Hiroshi and Wineland, who won the Nobel Prize in 2012 for their contributions to single photon and single ions towards this field. And so that is one concept you can keep in mind a little bit, which is superposition. Okay. Then comes the concept of entanglement. And this is something I think Soumya and others will tell you in the lab if you're visiting. And so what is entanglement? Of course, the idea is to give you a flavor. Otherwise, we could spend 24 hours. And people who know me know I can do that. So this is a popular example of what is called the Schrodinger's cat. And for some people who watch sitcoms, you have watched The Big Bang Theory, maybe. I don't know. The students, maybe you have. So you've seen that get even popularized in The Big Bang Theory. So what is this Schrodinger cat? Well, there is a cat. He or she is sitting inside a box. I would say he, because there's a probability of the cat being dead, so let's call it a he. So there is a cat sitting inside a box, and there is a vial of poison inside the box, okay? So if the cat has this poison, of course, the cat, not intentionally, this is not a suicidal cat, it's an experimental cat who has a poison and kind of dies, and if he doesn't have the poison, he lives. But if you're sitting outside the box, literally and otherwise, and it's a black box, in this case it's a green box so that you can see the cat, but if it's a black box, you won't know whether the cat is dead or alive, because the cat could have had the poison, not had the poison, you don't know. So this ambiguity is captured in superposition, right? So it's a superposition of being dead and alive at the same time. So this is the Schrodinger's cat, okay? So what does it have to do with entanglement? Then comes in another character, which is a radioactive particle, okay? So if the cat has this poison, the radioactive particle is emitted from the box, okay? And if the cat does not have the poison, then the particle is not emitted. So of course the cat is happy if he hasn't had the poison, and he's kind of dead if he has had the poison. So what does this tell you? It tells you that even from outside the box, by just seeing whether you get this radioactive particle come out or not, you know the position or the state of the cat. So the state of the cat is entangled with the state of the radioactive particle. This is what is entanglement. So by actually measuring something, you know of the state of something else. This is what captures entanglement. The Schrodinger's cat is a good example because it tells you about superposition and entanglement in the same example, right? And so what the example that I really like is that of an orchestra. So, for people who love music here, you would know that if you go to hear an orchestra, you hear the cellist and the person playing the violin and the pianist, all of them are playing together. And you hear this beautiful piece of music which you enjoy as some symphony. But suppose you start hearing them individually. First you hear the piano, then you hear the violin, then you hear the cello. They are beautiful, of course, but together they create something which is a symphony. Otherwise, they are individual pieces of music. So entanglement is like this orchestra. So when you have entanglement, the whole is more than the sum of parts. There is a correlation that is shared, which cannot happen individually. You cannot write it as a product state for the students here. You can only write it as something which only exists as a whole. And this correlation is used in computing, communication, and various other applications. And in fact, we have some beautiful experiments on this, and I think Komudi and Soumya and all will talk about it in the lab visit, right? So what do we do? I mean, what is it that we began, let's say? So when we started 10 years ago, there weren't labs which were working on using photons towards quantum information. So this is what we started. We started making single photons. Now, when I say that, it seems like, we are in some cooking competition or something and we are making things. But believe me, it's much harder than that. As again, I won't take your name anymore. So, it's not easy to make single photons. It's not like, you're in a room and you keep making it dimmer and dimmer and you have single photons. It takes more effort than that. So there are different ways of doing this. You can use nonlinear optics. You can use solid-state devices, many approaches. And so, in fact, this is a review article that I was invited to write. And as is my habit, I roped in all my students at the time to write this with me. And so this is something which you can read if you're interested to know more about how to, make these single photons, which is what we do, right? And going on with my people story, the first person who comes to mind is, of course, Devadrita. She was the first student to join experiments in my lab. So, she joined in 2013, so you can imagine, because, that is when we started doing experiments, and was around for a few years after that in various positions, and in fact was the first person to get single photons from the source. And so she is currently in Göttingen in Germany. And so this is a picture from the lab of our SPDC cones. Okay, so this was one of the early things. As I said, one of our main focus areas is on fundamental tests of quantum mechanics. And so in this, we have done a lot of work on finding correction term to the superposition principle. So you already now know a little bit about superposition. What we did is we found a correction term in theory and then followed that up by the first experiment where we measured this. And of course, going by our style, we didn't measure it inside the lab. We went 100 kilometers from here, bothered all the staff at Gauri Bidnur, who I would like to acknowledge, and set up a tent there and literally did the experiment in a tent. So a precise experiment in a tent was, of course, something that still remains very special to us. So Rengaraj and Prithviraj, who were both students at that time, who were doing their internships and project assistant and so on. Currently, Rengaraj is in LMU in Germany. Prithviraj is at QuIC in Vienna. And so both of them led this experiment. And Surya, who had just joined at that time, and as a PhD student, gave them able support. And so this together and of course we have our collaborator Somshekhar, but I have chosen this to be a student talk. So the pictures are going to be of the students here. And so this was a beautiful experiment. And of course, lots of frantic calls at 2 a.m. and 3 a.m., because the experiment happened at night. It's a radio-friendly zone. So in some sense, you can't take phones and so on. So you have to come back to the guest house and call. And then very nice stories here. Here you can see the cornfield here. So there is a cornfield. So they used to cut the corn and then, have that for snack. So lots of anecdotes on this, and a beautiful experiment emerged. So this was, I would say, one of the first experiments on fundamental tests of quantum mechanics from the lab. Then, of course, we have been actually very blessed that not only have our scientific peers acknowledged and appreciated what we have done, there has been a lot of appreciation from the other people as well, the popular media. They have taken up on our work, and that is something we consider a privilege, because I think that is how we may be able to reach out to more people than the little community which we represent. So a lot of coverage happened on these theory and experiment work on the superposition, and and this was the experimental schematic. Okay. The other genre, of course, the very important genre we represent, as I mentioned, is entanglement. I already talked to you a little bit about entanglement. So we do several things in entanglement. But of course, if you have to do several things, you have to make an entangled photon source. And Ashutosh Singh, who you can see here, was my first experimental PhD student, who also made the first entangled source in the lab, and arguably the first one in the country. And so this is his entangled source. You know, this picture, Ashutosh has annotated it. I always use it. It's a beautiful source. It had very high fidelity. It's the first one. And lots of work emerged from this on measures of entanglement, sudden death of entanglement. In fact, he set up the experiment which we are now finishing on manipulating the sudden death, making it happen later, or not at all. So this is a series of work that Ashutosh was involved in. Then, of course, going slightly to fundamental quantum optics domain, okay? Of course, it's in the fundamental regime, but now we are talking about quantum optics. This was an experiment which we are very, very, you know, we are very biased to, I would say, because it involved so many people. Siman Raj, who was my first PhD student in the theoretical domain, turned an experimentalist for this experiment. So he actually led this experiment, which, you know, was finished with help from QuIC and Devadita. Siman Raj is now at University of Pavia in Italy in collaboration with Fermilab, and QuIC is currently at NCU in Poland. He will be defending his thesis on Friday, so you should come to his talk as well. So this was the team, of course, with external collaborators and others, and we showed that a very, very ubiquitous phenomena in quantum optics, which is called the Hongo-Mandel effect, can be shown using classical pulses. So we have this tendency of kind of challenging textbooks as we go along, and this was one of those things that, you know, what is written is not quite right, and so this is what emerged as a result of that. In the same genre, but with a little more quantum information focus, we did a very nice experiment where we came up with a new technique for estimating the quantum state, bypassing the standard technique called quantum state tomography, and of course with collaborators, but the students who contributed to this are, of course, Surya and Shonchari, who are, of course, still here. And so then this one, you know, this was our central question, that can we have a device with which, without any change of internal settings by the user, we can determine the quantum state of the system, which is something which wasn't thought of before, and we answered this through this experiment, which worked out very well. Again, you know, we also received quite a bit of appreciation for this experiment, and you know, in fact, we are very excited that this might lead to a portable quantum state estimation tool, as we have predicted in the paper. Again, in the same genre of fundamental quantum optics, quantum information, one of our recent results is on a loophole-free interferometric test of macrorealism using heralded photons. Now, this is a very mouthful of a title, but what it means is that we have challenged the notion of reality as you know it and said that that is not quite true in quantum. So the fact that Mr. Varadarajan is sitting there, if I were to look this side, I think he would still be sitting there. Let us assume that that is true, but in quantum that's not true. In quantum, what you see is dependent on what you measure. So the thing does not exist. Reality as we know it does not exist unless you measure. So what you see is an act of measurement. And so we performed the first experiment which actually proved this without any loopholes and ambiguities. And so this is this LGI experiment. And yeah, again, something which was much appreciated. Now going on to another genre, which is on generalized measurements or weak measurements. Now this is something which you'll find very interesting, because if you heard about quantum, you would know that measuring destroys the state. Something that we talk about even if we are not from the field. That, you know, if I see it, then it's going to be destroyed. But then, of course, there is this genre called weak measurements, where by doing a statistical ensemble of measurements, you know about things in between preparation and measurement without destroying the set, okay? And so this is something which we have applied to many different experiments and theory work. And of course, these two you have seen. This is Gaurav, who was a project assistant with me, and is currently at University of Oklahoma in the US. Okay, so this is a series of things we have done in this topic. Going on to our approach to quantum computing, which of course, is a focus area. And this, I think you will hear about a little bit in the lab when you visit, if you visit. Instead of working with two-dimensional systems, so let me just see the time here for once. So just, so another 10 minutes or so. So instead of working with two-dimensional systems, what we are doing is we are working with more than two-dimensional systems. And so, of course, why are we doing that? The idea being that, if you have a game of football, let's say, and I don't know, Subbu seems like the athletic type to me, so you may be someone who plays football. So maybe there are 4 different outcomes you can have for the game. I don't play. So you could win, you could lose, maybe you could just go on playing and then the time is over, so you have to abandon the game maybe. Or maybe it is just washed out because of rain. So 4 possibilities emerge in my mind. So how will you declare this using a quantum system? You will need 4 states to do that, as simple as that. But if you want to use qubits to do this, which are 2-dimensional, you will need 2 of them, because each for 2 results. If you have a 4-dimensional system, you can of course declare it with 1, right? So the idea is that by using a smaller number of systems, you can actually have a lot more information packed in. And this is what we are doing in quantum computing, okay? And you will see a little bit of that as you go to the lab, if you do. And this is a technique which we have, established. We founded this and showed that it works very well. And these are the 2 who contributed to quite a bit of the work here in this genre. I'll skip the details of this, but having said that, we're very excited by, some of the new results which we have, in which we have been able to show that these 2 qubits that we have in the lab are actually nearly maximally entangled, and we have a new way of measuring them. So something we are very excited about, and all the prospects of, applying them to different gates and protocols in quantum information as we go along, okay? And in fact, this is, again, an article I wrote, which we have some copies of. If you're interested, you can take them from the lab. Then, of course, coming to the last part of, what we do, again, giving a very bird's eye overview. One of our main areas, of course, is in the domain of quantum communication, okay? And what is quantum about this is the key distribution problem. And it's the most quote-unquote practical quantum technology. Why is that? Because Mr. Suresh can perhaps have some QKD happening in his cell phone. So we don't need to be very rich or very famous to use QKD. We can buy things off the shelf. So it's practical that way. And in quantum computing, we have a little way to go for that, for us to afford it as normal human beings, okay? But why you should worry about it anyway? Why should you have it in your cell phone? So now, these are 4 things: purchasing through credit card, banking online, voting, and then defense strategic communication. Now the first 3 things, Savita helps me do this all the time. Without her, I wouldn't exist at RRI. So then, the things, can we do this through Naresh's credit card? Instead of waiting for this big PR, institute credit card can we use? We do this all the time, right? Buying things. But then suppose it's an institute credit card, and instead of me and the bank, a third party gets to know the number or the information. Of course, whatever, now I will leave it to accounts and purchase to figure out whether we are rich or poor, but then we don't want that to go to a third party. This is strategic communication. It only is between the sender and the receiver. You don't want a third party to come and know this and take away whatever little or more money you have. And that is what would happen using the current way in which we are doing this, okay? So this is called classical cryptography, what we do, and we have a problem with that. Why do we have a problem with that? And now I will, let's see, Jacob, what is 3 times 7? It's not a trick question, unlike Ashleen's questions. Hopefully you're thinking and saying 21, right? But then, now, if I ask Ashleen, what are the prime factors of 113471? You won't know this. Because it's the reverse problem. 3 times 7 is multiplication. Factorization is the reverse of multiplication. But they're not the same category of hardness. One is much harder than the other. And that is what we are basing our security on. So now what we have now is this thing coming up. What is coming up? computational resources are growing very fast, and today's hard problem could be solved tomorrow using brute force attack. We can have new algorithms for classical computers. We have the quantum computers, which are very real now, which will run Shor's algorithm and kill the problem, the hardness class of the factorization problem. So my security should be independent of future advancements in computational power, new algorithms, new technology. It should be future secure. Example that I like to take is that if I have a little bit of money left for my daughter, she should get it 20 years down the line. She should inherit some resources. But that won't happen if we leave this on classical cryptography. Why? Because even if the thing comes in 30, 40 years down the line, it will break the security of today. Our current way of keeping things secure is not future secure. So we need a solution which is future secure. And that is quantum cryptography, which is what we are working on, okay? And the one thing you have to remember is we need 4,000 qubits, 100 million gates in order for this to be a real threat. So some of you would say, when I first joined RRI, a dear colleague of mine said, what are you working on? It won't even be possible in our lifetime. A dear colleague who now is working on quantum information. So, this is the change that I have seen in 10 years. And so, don't worry, this will happen very soon in most of our lifetimes, because I'm sure, we live for a few years. So don't wait for something to become a problem. Solve it now so that it's not a problem. Because of course, quantum computing will do amazing things. You don't want it to break your security. And so these are two things which go hand in hand. Quantum computing and quantum communication. They feed into each other and help each other grow. And so that is what we are working on, these two aspects, right? And of course, we are working on different things in it. We are working on India's first project on satellite-based quantum key distribution in collaboration with ISRO, quantum experiments with satellite technology. We are working on chip-based QKD under the DST ITPAR program. We are working on quantum teleportation, which is another way of quantum communication. It is not about teleporting a human being, as is shown in science fiction. It's about changing the state from one body to another. The human or the object doesn't move. The state goes from one side to another side, and it could be over thousands of kilometers. Okay? And we are also working on what is called device-independent random number generation, something very interesting, and we are very happy that we have a Center for Excellence in Quantum Technologies now, and the RRI wing, we are heading the RRI wing with these projects. Okay? So this is our overview, and it's a people talk. So of course, these are the various people, plus one or two who are picture shy, who are working on different quantum communication experiments at RRI. And of course, some of them you see here. Some of them have been around for some time. Some are as new as last week. So it's a very, dynamic group. Very, very happy to work with this whole group on all these different experiments that I talked about. Yeah. And these are the past members who have contributed to this, Nagalakshmi and Rakshita. And you've met Kaushik before. Right, so we've done different types of QKD protocols. We've done our version of BB84. We have done a new version of the B92, which is very interesting because we have a higher key rate and a lower error rate than the best known till then using this SPDC technology. So we have 50 kilobits per second and a very good QBA, which is information theoretically secure. And we have done entanglement-based QKD. This is things you will see in the lab. I think Shourabh, Satyaranjan et al. Will tell you about things if you're visiting the lab in the afternoon. This is our entangled QKD experiment. We achieved very good entanglement. So one thing that is important is, of course, when we are working with something, the amount has to be high enough, otherwise you have security compromises. So we achieved very good, amount of entanglement, which is quantified by this. This was this is a paper which we wrote, which is, in fact, an in-lab free space QKD protocol, which we are very happy to say is our country's first reported end-to-end free space QKD experiment, which has been published in an international peer-reviewed journal. We are very, very excited by this. And of course, you've met the people in earlier slides. And in this, we also have a new patent application now. Okay. So we've done something very interesting, which is not experimental also. And this was serendipity. So we wanted to simulate And then we realized we don't find the simulator online. Then we started making one. And so there are different simulators available for QKD, but we are experimentalists. So what we wanted is that when we are simulating something, it should not be perfect. We don't like perfection. That is obvious if you meet us also. But then, perfection is unreal. So when you work with experiments, the devices don't behave the way you think they do. The processes are also different from how theories predicted, right, Anindya? So then we have to know and allow for the fact that imprecision exists. So our simulation toolkit has these imprecisions. So it takes into account the fact that these are real experiments done by real experimentalists with their own shortcomings, right? And so this is what we did with QKD Sim. And again, we got quite a bit of appreciation for that. All this is towards long-distance quantum communications. As I mentioned, if, for instance, I don't know, Mr. Nagaraj and I are communicating with each other in this room in a quantum way, it's fun. But then that's not the end of the story. We want the countries to talk to each other, because that is where strategic communication matters. We have hardly any secrets. We talk about our research as openly as we, it's always like that, right? So we don't like to keep secrets, but countries do. And so then that is where the real fun is, in long distance. And of course, Isaac Asimov, who you know is a science fiction writer, very famous one, he said that today's science fiction is tomorrow's science fact. And so this couldn't be truer than our project on satellite-based QKD. So at first, fiction became science fact very quickly, and it continues doing that. It's not easy to do long-distance communication in a normal way. So if Naresh and I start communicating, beyond a point, we won't have line of sight, because the Earth is round. You will not be able to keep seeing each other. The horizon is a problem. So, and if you use fiber, it will have, lots of losses. And you can't kill the losses like a classical way, because you can't copy an unknown state. So then we have to think out of the box, literally, out of Schrodinger's cat's box, right? And come up with new ways of doing this. So satellite is one, and another is quantum repeaters, and we are working on both these topics, yeah? So what is the idea? That a satellite, it spends some time over one ground station, exchanges something, goes over to a next one, exchanges something, and then we have a key established between two locations which are thousands of kilometers away. So this is the general idea. And of course, the big picture, if we live to see this, will be a network where we have the satellite connecting certain ground stations, and then, fiber connecting various service providers. So this is the big picture. Many countries are working on different aspects. We are working on this from 2017. And of course, our aim is to establish information theoretically secure quantum link between two Indian ground stations using an Indian satellite as a trusted node. And so this is the main aim of this project. And if you go towards our end of RRI, you will see our portable ground stations. This is one of our domes. And this was an experiment we did in January 2021, which was a free space QKD experiment between two locations, which were, this is our lab, and this is the nursery cabin. RRI, as you may know, has lots of trees. And we love the trees. But then we, of course, don't want to cut them. So it's very difficult to have a free space link where we don't have a tree, in the way. And so this was the one link we found where this didn't happen, and this is the distance over which we were able to do this, which was around 50 meters. This was also India's first free space QKD experiment using an atmospheric channel between two stationary source and receiver. And now we are increasing the complexity of the problem. I think Durga et al. Will tell you a little bit about what we are doing if you go to the lab. And we received some appreciation for, our ability to have done this first and sort of setting the way for the future. And we also received this very nice recognition as one of the 20 major success stories of the Department of Science and Technology in 2020 for both our quantum state estimation work and the QKD work. And India Science, which you all should go to, read. It's a very nice online forum where they talk about science in India. So Vigyan Prasar, in collaboration with India Science, recognized us as one of the top 10 innovations of 2020. So this is our beautiful building. So what I would like to say is, so this has been a journey. As I said, it has been a journey which has been enabled by people. So it is the past, the present, and the future. People who would make things happen. So if we are here 10 years down the line, I'm sure there will be a new set of faces which we would see. But having said that, we are very, very privileged and honored that a journey which we started 10 years ago with questions like, is this science fiction, or will this ever be possible, you know, and of course, converting a storeroom to a lab is going this way, where we have been able to do very nice things, you know, in science and technology in this domain, and also find ourselves, you know, in providing the lead at national and international fora now, thanks to the hard work and motivation that the students and other lab members have had. So I think the 10 years is basically dedicated to these people. And the next 10 years, I can see some people here who I would be talking about 10 years down the line. So this has been our journey. So thank you very much. And of course, future is bright and in quantum. So thank you. So, Ashleen, the floor is yours. Yeah.
That was very holistic and concise. Thank you, ma'am. Thank you for your all beautiful words. And that was a beautiful way which we see the journey and milestones of this 10-year lab. Thank you very much, ma'am. And now again, I would like to call Urvashi ma'am to share the messages of all the well-wishers who has sent their message on this special day.
Right, so thank you again, Ashleen. This is a very special section, I believe, because of course, you know, as it's a people talk, I'm very, very happy that some people have shared their, you know, messages with us to actually read out to you guys today. So of course, the first one is from the current director of RRI, and then we have past members from the lab who have shared their, you know, words with us. So I'll take a few minutes to share this with you. So message from Professor Tarun Shauradip, who's the current director of Rahman Research Institute. Dear Urvashi, thank you for the invitation. I will be in travel back from Pune tomorrow, so he wrote this yesterday. So he's traveling today. As many of you know, the volleyball team organizers, they know this, through the entire period of the event, and he regrets that it will not be possible to join in person or even remotely. Please convey the following message to the group. And so this is the message. Heartiest congratulations on the 10th anniversary of the QuIC lab. I'm writing to convey my appreciation of the impressive work carried out by the lab and its generations of students and staff. My best wishes to QuIC for the years ahead. Best regards, Tarun. So we would like to thank Professor Shauradip for his kind words, and we of course miss him, but you know, hopeful that you know, we will be able to share such things with his presence in the future. So thank you very much. Now I go on to some messages which the past members have sent me, which they would like me to read out. The first message is from Ashutosh Singh, who is now at University of Calgary, Canada. Dear ma'am, this is truly music to my ears that we are celebrating the 10th anniversary of the QuIC lab. Time flies, but not memories. Congratulations to all the current and previous lab members, and especially you as PI of QuIC Lab, which has achieved several feats in all of these years and has established itself as one of the preeminent labs in photonic QIP. My journey at RRI and QuIC Lab as a PhD student has been truly amazing. That has contributed significantly to my career growth. I wish you all the very best in your endeavors and great success in your careers. May you all achieve the sweetest dream of your life and fulfill your aspirations. Wish you all the best, Ashutosh Singh. This was a very, very heartwarming message, and I of course wish Ashutosh that he also achieves the sweetest dream of his life and fulfills all his aspirations. Our best wishes are always going to be with him. Now I go on to a message from somebody who's soon to be doctor on Friday, Qkd Experiment, who's now at NCU Poland. Respected ma'am, congratulations to you and all the past and existing lab members for achieving this milestone. I feel proud to be a part of QUIC Lab, which has been one of the leading research facilities working in the field of quote-unquote anything quantum. I feel privileged to be able to work on various exciting quantum experiments during my PhD tenure. I also cherish the memories with all my lab mates who are both exceptional scientists and extraordinary friends. I heartily wish for the success and growth of this lab. May the force be with you. Sincerely, Qkd Experiment. So of course, I wish him all the best in his future for his Viva, which is on Friday, and may the force be with him always. Now I go on to a message from Devadrita Ghosh, who's at Göttingen, Germany. This is a slightly longer message, but I'm quite sure that you will enjoy hearing it as much as I enjoyed reading it yesterday. QuIC Lab, the name which is always very close to my heart. This is partly because when I first saw her, she was just born. And then I experienced her day by day while she was growing. But mostly because it gave me the opportunity to learn new things, to face unseen challenges, to acquire the knowledge of both optics and quantum mechanics, to work in a group, to be patient, to not to lose hope, to celebrate the success. And how time flies. Today, 10 years have passed. I'm really happy that I get this opportunity to convey my feelings. It is really hard for me to say something which is coated with my deep emotions and sentiment. I adore the name, the logo, and the theme of research, the place, and overall the group. Though I'm physically away, I still feel that I'm part of this lab and its initiatives. This is because I met some of the people at this lab who I am still in touch today, and I know they are always there when I need them. I still remember those days when we used to level the cupboard, organize the stuff we purchased, and learned how to deal with the Teisophire laser. Oh yes, I love that laser. I can see that day when we first saw the single photons, succeeded in coupling photons into the fiber, and observed the coincidence peak. It is not like there was always happy days. Days passed when we did not achieve the Hongo-Mandel dip, and then one evening, I still cherish that moment, we observed the famous dip. I know it seems so obvious now to observe those, but on that optical table of the QUIC lab, when I first observed those, that instant was not any less than a eureka moment. We also spent quite a few days seeing the three-slit pattern with single photons. I remember asking Ashutosh, "Count Mila?" And he, with his sad face, "Kahan count?" But finally, he finished the experiment with great results. And ma'am was there, always, while building it up with all her efforts, providing us all the resources we needed, and giving us the care and support when we needed that most. I truly admire the spirit that has been maintained, that it was never about I, but about we, be it a moment of failure or success. I confess that I really miss that we, and always will do so. There were tea breaks, there were pizza parties, there were birthdays with cake, there were enthusiastic visitors, there were conferences and yes, food, there were new experiments, there were challenges and thrills, there was despair, and then there was also hope and joy. I really wish I could taste all those flavors once more. QuIC Lab, I truly wish all my best wishes and love, and thank you so much for getting the opportunity to be a part of it. Of course, I would like to thank Devadrita for being a part of QuIC Lab. I think her positivity and her attitude towards her work set the tone for what our lab is and has been. And I wish her all the best in what she does today and in the future. And finally, from G. Rengaraj, who's now at LMU, Germany. Dear ma'am, many thanks for your invitation, and it's my pleasure. I want to add the following lines. The RRI QUIC research environment and consequent interactions with my peers and advisor provided me with a toolbox of different skills that has paid dividends in my research career and professional relationships. Best regards, Rengaraj. So I again wish Rengaraj all the best, and I'm sure he'll have a fantastic research career ahead. So these are the messages which I received yesterday and today morning, and I'm very, very happy to share them with you. And it was wonderful reading them, and of course to all of them and to everyone who has been a part of the lab till now and currently is and will be in future. It'll always be my best wishes for what you do. So thank you very much.
Thank you all for the support and blessings for us. And the most awaited moment, the prize distribution. Let me take a few minutes. So the winners. And the first prize goes to Cyril Benny from LAMP. He has scored the more. And now I invite Vasudha ma'am to hand upon the prizes to Cyril Benny. Ma'am, please, and Cyril, please. Excuse me, Cyril, a photo. Ma'am, can you please wait to take a photo? No, just ma'am, for the... Thank you, ma'am. Thank you very much. Next, I invite Naresh Shah to give the second prize. That is for a team consist of Sri Lakshmi and Sharon. They are also from the LAMP. Sir, please. Thank you, sir. And there is a special prize for participation. Now I call GB Suresh sir to give the prize to Suresh Varadarajan. Special participation prize. Yes, sir, yes.
And I think I wanted to just give some tokens to Ashleen. For Ashleen, Mehak, and Soumyaranjan, who have played a more important role in organizing this, because I didn't do much other than prepare a little talk. So this is for Ashleen. Yeah. Where is my... Wow. Mehak. And Soumyaranjan. I look forward to a good lunch.
Thank you, ma'am. Thank you all. And once again, I'm reminding about the lab visit. We have lab visit from 3 p.m. to 4 p.m., the first slot, and the second slot from 4 p.m. to 5 p.m. If you are not registered, don't worry about it. Just contact Mehak, and you can inform her about your slots too, 3 p.m. to 4 p.m. or 4 p.m. to 5 p.m. And all are welcome. Once again, I'm thanking all of you for your support and being here for this celebration. Thank you all. Thank you for your support. Pardon? Yeah, answers. You want answers for who am I or the other one? Both answers. I think the catch me if you can come to me. I can show the answers to you. Yeah, else we'll send you the mails. It was not only the SI unit. I have included all the units, like Newton, candela, and meter, kilogram, everything. I have mentioned it specially, not only SI units. Don't you guys remember? In this thing, it was 15 I added. Okay. And nobody has crossed more than 6, I think. 6 or 7? Okay. 7 was the maximum. And now about the questions. Yeah, you cannot do quantum mechanics unless you are in my space. Yes, Hilbert space. And I am not the crocodile hunter, even though mine and his name sound similar. I made our feline friends popular among physicists. Who am I? Yes, Schrödinger. Feline friends maybe caused confusion. It's cat family. And next one. Maximum speed in a piece of wood. Who am I? I think you have considered like maximum speed. It's related to his name. That's Max Planck. Okay, the next one. Put charged particles in a uniform magnetic field, you get my levels. Oh, sorry, I may have already told you my name. Who am I? Yes, Landau levels. You should have come earlier to participate, right? Okay, next one. This you should have answered. I expected everyone to answer this question. It's a very famous scientist. Not only, I couldn't say her that a scientist, she's both physicist and a chemist. That's, I am a unit, I have an element, the unit measures a quantity of the element. Who am I? Yes, Madame Curie. And the other one, which is very basic, which we have all learned in 8th standard, I think NCERT book of 8th standard have special mentioned about it. It's people weigh things on earth, I weigh the whole earth. Who am I? There is a famous experiment in his name too. Let me say, Henry Cavendish. Yeah, now I can see the expressions of people. Thank you very much all once again, and thank you for all the cooperations. Thanks a lot. Hope to see you all in the lab visit, all these faces there. Thank you very much.
Thanks a lot. Thank you very much for coming, Mr. Suresh. Yeah.
May not be different. What Jacob sir was telling that some